Oops, I didn't realize the oscilloscope wasn't being captured, the function generator and oscilloscope video. But I realized OBS has the ability to capture those windows of the oscilloscopes, which is pretty nice. I thought everything was all drawn in one layer. My bad. First time recording all this stuff. And at the same time, I can move the oscilloscope all around the page that I want, which is crazy. I mean, it's independently controlled in OBS. So multisim, thank you. So we have what we call a level converter. This basically takes a roughly 4 volt peak to peak square wave and amplifies it up to around, what does it say, 22.6 volts peak to peak. Why would you do such? Testing transistors, simple transistor checker circuit. Or if not, you just simply want to turn on a transistor very hard. And in this circuit, we're using what we consider a computer power supply through a 10K resistor, because it's your general pull-up resistor for your 5 volt and your 3 volt systems. we're kind of mimicking the same type of circuit, you know, but we're at 19.5 volts just because you could do this circuit in real life and you'd be like, whoa, my God, you know, that's a huge square wave. The reason we did this back in the day was we needed bigger square waves from Arduinos to turn, you know, you want to be able to turn on something a little bit harder, and you're like, hey, which circuit works, which one doesn't? To me, a lot of these ones that you found on the internet, yeah, they're okay, but as you can see right here, you know, these are the Mac Daddies. And in this circuit right here, I like it because you can actually test the circuit beforehand, kind of get an idea. That way you're not blowing up components. Like, for instance, if you look at the 2N22A, you're pushing around, what is it, 974 microwatts, which is not bad, you know. Very little heat, you know, through a 10K, and you're producing, I'd have to say, some of the most gargantuan. In fact, here, let me get these ordered correctly on the screen. I mean, that's how easy it is in OBS. And keep in mind, I'm not moving these oscilloscopes in the original window. I'm moving them in OBS, which is just crazy, you know, when you're doing the stuff. But it'll work. And here it goes in action. So you get an idea in the Christmas motif here. Let's change this line to straight up green as for the Christmas colors. And you can look at the divisions on the oscilloscopes. If we're at 5 volt per division, we're off the chart on the output. You know, so we're on a 10 volt division on the output, and to me, directly linking. And then what I also would tell you about the circuit has a very special feature, or I should say function, built into it. And that is, this circuit, when transmitting intelligence over it, is what we call DC stable. In other words, the interference on that line will be almost zil to none, because there is roughly 9.75 volts continuously on that wire going out, which makes it pretty much impermeable to RF interference or frequency interference or crossover, crosstalk, or that type of thing. So that's another feature of this circuit, because normally what these circuits are used for is buffer circuits, going from one board to another board. You know, granted, they'll have caps involved, and you know, because they're doing AC analysis, you know, AC amplification, not analysis, but AC amplification. But they're using a DC circuit to transmit an AC signal, but they do it without any type of hum or zip or buzz. And that's one of the creature features of this, you know, circuit that I was wanting to illustrate, was the fact that you could build it, see what it looks like before, you know, you do it in real life, and you'd just be like, wow, you know, you're looking at roughly a 13.8 volt output square wave, you know, 1 kilohertz, which is pretty cool, and it's pretty clean. But keep in mind, the smaller the feeder resistor is on this side right here. So this guy right here, you can see we're using very little wattage, or very little power for this resistor for, you know, for amplifying that monster wave, depending, you know, on the load, which to me is not good. There isn't going to be much load right here, except for what's going through that 10K when you yank on it. But the idea is this circuit operates in what I would consider buffer mode. And pretty, like I said, pretty crazy to see this, look down and see a schematic like this and amplifying an AC sine wave across it. But strangely enough, they did. And they did it a little bit different. We're basically in a class A bias slash the signal generator is turning on the transistor. But it does it cleanly. And like I said, if you take a 10K and you go down to, like, say, 100 ohm resistor, you're just going to get smaller waves, but cleaner. In other words, it's a less transition time. You can see we're getting spiked here on the second oscilloscope, or SC1, but it's really the second output of the oscilloscope. It's the PRA, interface. But back in the days, we were trying to amplify 3 volt to 5 volt, and these circuits were used. You could technically work. This supposedly amplifies its frequency cutoff or amplification cutoff would be around 500 megahertz, something like that. Just look up the specs on the 222A or the 3904. It'll tell you what the cutoff is as far as frequency wise. But they would be used in just general testing circuits, getting an idea of, hey, how do you amplify a square wave in the year 2022 using multisim? It's not easy, when you look at it. Using input resistors, output resistors. Normally this circuit would have a 100 ohm output resistor or 470 ohm output resistor for its protection's sake, in a sense. But to me, we're just illustrating how the hell do you amplify a roughly 4 volt peak to peak square wave to 22 volts peak to peak, and that's coming off a 19.5 volt power, laptop power supply. We're basically mimicking a power supply. But to study stuff like this, that's what we use this stuff for. Hey, we're just like, hey, for educational purposes, how do we not blow up a 2N222A? And plus that it helps us substitute resistors without having to unplug a solder or do any soldering. And breadboards work great, but what we've noticed when you're doing a lot of AC analysis on breadboards or EFI fielding, we generally don't use the breadboards for doing that because a lot of the capacitance from that board will creep into our circuits. So having something like this is like the bee's knees when it comes to, doing something pretty phenomenal. And I'm pretty sure that the square waves are going to look like that coming out on a regular, regular circuit in real life. Just keep in mind, if you try to do any smoothing with, resistors or capacitors, you run into what we'll call the RC time constants or resistor capacitor constants. Hey, this is how long it's going to take to discharge before it recharges and stuff of that nature. Most stuff, when you run into the high frequency square waves, will have picofarads and nanofarads being utilized with it just to clean up the signals. Like a lot of the button switches didn't understand, like a lot of these people when they were building circuits for toggle switches and they're using those regular press buttons. They would get what we call noise in, bounce, debouncing of the switch. You would see it on the output, and in order to get rid of that debouncing, you would normally put, a nanofarad or picofarad cap across it, your choice, and that would keep the debouncing, one, press per click. So that's something for those old timers, they can appreciate that. And, hey, we've got 2 oscilloscopes, illustrating a simple NPN transistor doing what it does best. And it doesn't sit there and waste a whole lot of wattage. I mean, we're in the microwatt levels, and generate monster waves. It depends on how much for the output. What kind of load are you going to be loading with the circuit? But needless to say, that if this was coupled into another circuit to continue the transmission of the square wave, it could be. Granted, you have your delay times, but keep in mind, anytime you pass a signal through resistors or capacitors, you're going to delay stuff. But this is just a simple, how do you amplify a square wave, using a transistor and a laptop power supply, and if need be. Granted, you could go all the way to 30 volts. You could go all the way to the top of your transistor's voltage levels. In other words, whatever the maximum volt level it says. If it says 30, you got 30. You put 45 in there, it could blow up. And that's what a lot of these things I like, is you get to see the stuff without actually having to blow it up. And when you put it together, it should work just like this does in the real world, except for, like, you know, you're going to see a lot more noise coming off of that green wire, the output of it. As far as in the real world, you're going to see a lot of different, you know, you'll see a lot of different stuff. And my oscilloscopes go, I have a 275 megahertz oscilloscope and a 100 megahertz oscilloscope. So I could do signal analysis, but I could care less too. I have the digital analyzers. They're there. SIP chips are basically sub chips that can do all the signal analysis on breadboards and stuff of that nature, so you don't have to use any of the oscilloscopes and analyzers and stuff of that nature. A lot of the computers could analyze these as long as the frequencies are down low enough. You know, for the SDR on capture would be, you know, whatever the sound card is. You know, 192 kilohertz. You know, sample rates, you're going to get a wider bandwidth of being able to sniff, you know, frequencies that are, you know, between 0 and, obviously, I would have to say around 60 kilohertz is what my cutoff was on my sound card, which is pretty cool. But, you know, that's another topic for another discussion. But to me, this is how you amplify, you know, simple square waves cleanly, cheaply, you know, pretty kit-wise. You know, so if you were running, you know, a square wave down a wire and you weren't trying to, you know, create too much, you know, ping through it, in a sense, the circuit would be utilized, you know, in short distance, you know, square wave, you know, transmission and amplification. Not bad, you know, but this is one of the circuits we ran into when we were dealing with Arduinos. If you want to do switching, or if you want to do, you know, turning on coils or inductive coils and MOSFETs and stuff of that nature, you can be doing lots of this. But we're doing it with, you know, transistors. Granted, most people do nowadays use MOSFETs, but this is about the transistor. So this is Multisim 14, illustrating a simple transistor amplifying a square wave pretty decently, cheaply, simply, and illustrated through OBS and its multi-window. I mean, the fact that you can make that window, wow, that large, is incredible. That's pretty good for signal analysis. Same thing with this one right here. You could sit there and watch the circuit. Hey, that's not bad, you know, especially if you're on a multi-output window. So thank you, Multisim, for having the ability to, yeah, integrate to OBS somewhat. So other than that, hopefully you found this video interesting, and if you're wondering how to amplify square waves, it's pretty straightforward to a certain extent, but it does have its caveats. You know, you're going to, just with RF interference, noise, it'd be pretty cool to see a 22 volt monster square wave coming off of something going, wow, look at that, for nerds and electronic people. Remember, this is an art. So other than that, hopefully enjoyed Multisim 14, illustrating a simple square wave amplifier. Have a good day.